But this talk focuses essentially on energy generation, energy consumption at the global level, the global warming trends, the digital ecosystem that we have, the issues with energy consumption, energy use in this system, the trends, and then what we can do generally to address some of the concerns related to the cost of computing from a carbon emission or greenhouse gas emission perspective.
Ever find yourself stuck with like 1% battery on your phone and no charger in sight?
The worst. Happens to the best of us.
Yeah, tell me about it. But hey, maybe today's Deep Dive can shed some light on a solution, pun intended. We're talking about Massoud Pedram.
Oh, now there's a name you should know.
Right, the material you sent over about him. This guy's a serious player in computer engineering.
Absolutely. He's doing some really groundbreaking work, stuff that can totally change how long our devices last. And not just our phones. Think bigger. Electric cars, everything.
Okay, now I'm really interested. So his bio, it's full of titles, professor, chair, fellow. It's kind of overwhelming, honestly. What's the deal with all that?
Well, those titles, they're not just for show. They represent serious achievements. I mean, we're talking prestigious awards, leadership roles. It's like the guy's a rock star in the engineering world.
Got it, rock star. But gotta be honest, when I see things like VLSI in his work, my eyes kind of glaze over. Can you break that down for me?
Yeah, no problem. VLSI. It stands for Very Large Scale Integration, and basically it's how they cram millions, even billions of tiny transistors onto those little chips.
Okay, so those chips that power, well, everything.
Exactly. Phones, laptops, you name it. And they wouldn't be possible without VLSI.
So is Pedram like the brain surgeon making those chips even smarter?
That's a great way to put it. But what he's really focused on is how to make those chips more efficient so they don't drain your battery in like 5 minutes.
You're speaking my love language. Longer battery life. Please tell me more.
All right, so picture this. You're scrolling through your phone, reading an article, not exactly intense stuff. Pedram's working on ways for the battery to actually recognize that and use less power. Then, when you fire up a game or something more demanding, bam, it seamlessly adjusts and provides the power you need. That's what he calls dynamic power management.
So it's not about just one thing, it's the whole system working smarter, right?
Exactly. And he's tackling it from both ends. How to design these chips to be more energy efficient in the first place, and how to actually manufacture them in a way that makes them even better. It's like he's thinking about the whole journey from drawing board to your pocket.
Okay, this has been a serious eye-opener. I never thought about how much goes into something as small as a microchip.
It's incredible, right? And the fact that Pedram's involved in both the research side and the practical applications, that's huge. He's bridging the gap between these cutting-edge ideas and the tech we rely on every day.
But this talk focuses essentially on energy generation, energy consumption at the global level, the global warming trends, the digital ecosystem that we have, the issues with energy consumption, energy use in this system, the trends, and then what we can do generally to address some of the concerns related to the cost of computing from a carbon emission or greenhouse gas emission perspective. I'd like to thank inputs from Dr. Mehdi Kamal and Dr. Sasan Raspa for this presentation. All right, so there's many different definitions of sustainability. If we focus on sustainable development, it is defined as the kind of development that would allow us to meet our needs at the present time without really sacrificing the future and reducing the resources that will be available to them in the future. So the important pillars of sustainability are, of course, social equity, economic progress and prosperity, environmental issues, and cultural sustainability itself. My focus today is on sustainable computing, which refers to a holistic approach that stretches from power generation to use to manufacturing of products and equipments and instruments and servers, to use of these, to end of life disposal of these equipment, and taking a full life cycle assessment view of the process, ensuring that we can deploy information technology resources in our society, in our digital ecosystem, in such a way that would be sustainable. On the top right here, you see from a well-known paper by Marshall and Toffel, basically what also is meant by not being sustainable. I always like to look at what we are not, so that we understand what we are. So an example of a non-sustainable behavior is what is shown as plot 4 in this graph. The ecosystem is functioning at some steady state level. Something happens, a shock to the system, such as COVID-19 shock that we all, I guess, experienced in early 2020 and even now to some extent. And then if the system is resilient to recover and go back to its normal functions, such as 1 or even 2, we are doing fine. If you end up with 3 or 4, probably not good. 4, definitely not good. And 3 means there is a significant loss of our productivity, our capability to produce services and functions and so on. And that's not an example of a sustainable sort of environment, whether it's economic, social, cultural, or what have you. So there are many different goals for sustainability. Some of these have a strong socio-economic aspect. Some of it has to do with the environment. I don't need to go through the laundry list here, but you can read and you'll see we refer to no poverty, zero hunger, good health, quality education, gender equality, and so on and so forth. Now, to achieve computational sustainability, there are many different approaches that one could use. I've given here a sort of a short list of some of the techniques that one can use to ensure improved sustainability in our computing infrastructure. Of course, first and foremost would be to reduce the energy consumption footprint of the IT hardware itself. And this, as I will explain later on, has to do not only with the footprint as the equipment and servers and devices are being used, but also when they are being manufactured and when they are being disposed of at the end of life. Try to use less greenhouse gas intensive sources of electricity. Avoid coal, for example, or other types of energy sources which emit a lot of carbon. Increase the lifetime of the IT hardware. By doing so, of course, we amortize all the costs in terms of manufacturing and end-of-life disposal over a longer period of time, and therefore the overall energy efficiency of the IT hardware looked at on a full life cycle basis increases. Then obsolescence management is another very important factor. Can we recycle? If we dispose of something, can we do it in a safe way so that the impact on the environment is minimal, and so on and so forth. Avoiding over-provisioning and over-design, which is a tendency that people have because we want to get the maximum performance out of the resources that we have, and we tend to over-provision And when the system does not meet the high performance that it was over-provisioned and over-designed for, then it's going to create a lot of waste in terms of the energy consumption. And then finally, runtime adaptation and load management, being able to respond dynamically to the actual conditions in which the systems are being used and adjust the behavior of the system in terms of, say, energy consumption versus performance level dynamic. So I thought to make things in better perspective, maybe look at the whole process, energy generation, consumption, the trends, and so on, before we can get into a little bit more details about the IT infrastructure and what we can do to make it more sustainable and energy efficient. So global, and this is a plot that shows the sources of for generating energy, all kinds of energy, electricity, transport, and heat, as well as electricity only, which is the one that we use in our data centers or charging our batteries and so on and so forth. So the trends are sort of consistent, showing that the dirty sources of the energy generation, which are coal and gas, to some extent. Gas is, of course, better than coal, but these are, and oil, these are the dominant ways that we generate energy today, in spite of the recent trend to try to move to renewable energy sources. All the renewables, including hydropower, probably about 25% of the total electricity energy source today. This is the energy consumption trend. Of course, energy consumption is increasing. Generally, you see dips when there are economic recessions or big shocks to the system, such as the COVID-19. It's not captured here, but the trend is generally upward, and you can see, again, by the source, what percentage is dirty sources of the energy that's being consumed versus renewable ones. The one on the right, the plot on the right, shows the consumption-based CO2 emission per capita versus GDP per capita. United States is has the top honor there. We have the highest GDP per capita, but also the highest consumption-based emission per capita. But things are improving. You can see from 1990 till about 2020 or so, U.S. has reduced its consumption-based emissions. Same with Japan, Russia, Mexico, but China, you can see, is an increasing trend, and many of the other developing countries are also in the same situation, including Brazil, for example. So that's a worrisome trend. The effect in terms of global warming is well documented and known. So this shows, for example, on the right side, the increased temperature in degrees Celsius from 1980 baseline to about 2020. And you can see this is in the order of 0.6 degrees, 0.7 degrees Celsius. And this tracks very well with the atmospheric CO2 that's present. So it's well documented and well tracked. And that's the source of concern for us. This is there was this recent meeting in Egypt, Sharm el-Sheikh Climate Agreement, in which U.S. came back to the fold, and some new agreements were made. But the fact is that if we don't make any policy changes now, we expect by the 22nd century, 2100, we will have an increased temperature of about 2.7 to 3.1 degrees Celsius. This is really bad. I mean, this would be quite bad if, in fact, this happens. So with all the pledges and the targets, 2.6 degrees, optimistically 2.1 degrees Celsius, so we have to really try to be concerned about and care a lot about the climate conditions going forward. So let's now look at the computing trends. This is historical cost of the computer memory and storage. This is another version of Moore's law in which the cost of building a transistor or a storage element is dropping exponentially over time also. And we can see that there has been significant sustained improvement of our basic computer memory and storage capabilities. And that has also given us computational capacity, which is increasing similarly. That's the better known, where there on the right-hand side is the better known version of the Moore's law. And currently we are at the level that we can do in 2021 or so in excess of 100 quadrillion operations per second in our fastest supercomputers. When we talk of sustainability in computing, what we really mean is a number of different effects, reducing the usage of electricity in data centers, but also in households and small server rooms, so that we don't have to pay for the carbon emission that's needed to generate that electricity, making sure that our devices last longer because you don't run them at high temperatures, and therefore their longevity, lifetime increases, and you try to generally minimize failure in the circuits and increase their overall usefulness to the customers, clients, and so on, because they have improved energy efficiency. So these are some of the benefits of the energy efficiency, even if you just look at it from the point of view of providing power either on an average or instantaneous basis to perform computations. Of course, sustainability goes beyond that. As I said, one has to take the full life cycle view to do this right. This is a well-known standard these days with respect to how you look at the emission footprint of anything, including computing. There are three different scopes defined. Scope 1 is direct greenhouse gas emissions. This is direct emissions due to generators, boilers, equipment, vehicles that are owned and operated by the entity, for example, Apple or Microsoft or Google or US government entity. Then scope 2 is the indirect greenhouse gas emissions from purchased or acquired energy from other sources. And scope 3 is other indirect greenhouse gas emissions because of the activities by OEMs and suppliers to the company that provide the various materials, products, components that go into the company's final product offering itself. Of course, the company has direct control over scope 2, but should and of course scope 1. But the scope 3 is something that there is less control by the company or entity over it. That's one way of characterizing the greenhouse gas emission, and I will use this when I get to analysis of how different companies in manufacturing or software services or what have you actually deal with these scopes of energy consumption and therefore greenhouse gas emission. So if if you look at our digital ecosystem, this is trying to summarize graphically, basically the trends that we see. Again, is well documented and generally used terminology that there is foundational trends, there are other first order effects, and then second order ones. So the foundational trends are the democratization of software, meaning access of the software services and products by anyone, regardless of their class, economic class, or gender, or country of origin, or this and that. Versus miniaturization of the miniaturization itself, Moore's law. But beyond that, in terms of beyond CMOS miniaturization that's taking place, and trends in computing power that's generally becoming more power efficient than before. And then this broadband connectivity that we have, for example, 5G, 6G coming soon, and so on. Cluster 2, first order effects, is proliferation of connected devices and machines, hardware being commoditized and used in many different other products. Basically, maybe I've seen the effect as a result of COVID-19, the IC shortages and how it's impacting everything, right? That you don't expect there's going to have so much electronics in it, but they do. Then services coming in and world really being digitized. Cluster 3 refers to the functional capabilities that are being provided, such as advanced data analysis, analytics, machine learning technologies that help with decision-making, prediction, forecasting, and more secure accesses to various types of data, either through encryption standards or through some other protocols such as secure multi-party computation and so on. All right, so let's now look at the computing hardware's life cycle. There are many different ways of saying this, but generally, at least first order effect, one can say you plan a product, you acquire all the parts, components that you need to build it and to put it into operation. Then you operate it. During operation, of course, you have to maintain it if there are service requirements or upgrades and so on and so forth. And then finally, one will have to decommission and replace the part. So if you therefore look at the phases in hardware life cycle, there is before use, in use, and after use. Most of the researchers in our community, at least, have focused on in-use phase of this in terms of power management or load balancing, power collapsing, energy efficient hardware, new architectures, new devices. Mostly in-use is the focus, but of course, before use and after use are quite important as well. And there is CapEx versus OpEx. OpEx really refers to the in-use. CapEx is mostly associated with before use, but to some extent also the after use. All right, so let's look at some of the processes that we use to manufacture our devices and circuits and systems. We use very complex, often very dirty and energy-hungry processes, from chemical mechanical polishing to etching to oxidization, chemicals being used for many types of chemicals, and some of these chemicals are quite bad, much worse than your typical carbon emission. And so generally, chip fabrication is essential. We must do it, but it is very GHG intensive process. because of all the material and process steps that is involved in producing a state-of-the-art manufacturing. EUV, extreme ultraviolet lithography, is actually quite energy hungry and dirty in many ways, much more so than when we are doing 16 nanometer or 22 nanometer or what have you, right? Processes. So in terms of the chip industry and carbon emission, these are data points comparing TSMC versus Intel, scope 1, scope 2, scope 3 type emissions. And you can see that when you look at Intel, its total million metric ton equivalent carbon emission is much lower than TSMC. And it's not because Intel production capacity is much less or number of employees are much less or what have you. It is because essentially the difference is in the sources of production of energy in the respective countries. In US, the sources of energy production are generally cleaner, much cleaner than in Taiwan, and so that creates a big differential between the two. The other reason is that TSMC is relying heavily now for its advanced nodes on EUV equipment, but they emit a lot more greenhouse gases compared to Intel, which has not gotten there yet, at least on a production basis. And so, but remember these numbers in the order of 8 to 15, right, is for the biggest chip makers in the world, right? And this accounts for everything, from pre-use to in-use to after-use. All right, so then let's look at data centers. They usually house tens of thousands, maybe hundreds of thousands of servers, very powerful servers, CPUs and GPUs and specialized accelerators and so on. And it's a very complicated setup requiring air conditioning, power distribution, power quality control, local generators, lots of batteries for backup systems, and so on. So data centers, this is the global trend, electricity consumption. Data centers are in the range of 200 to 250 terawatt hour, which is more than the energy consumption of Egypt or Argentina or South Africa, getting close to Indonesia and United Kingdom on an annual basis. So that puts it in the right perspective for you. At the same time, giving credit to us to some extent, developers of these technologies and solutions that go into data centers. You can see that from 2010, I remember I started working on a similar slide deck in 2010 for a date keynote speech back then, and the projections were really like it's going to go up. The data center energy consumption is going to keep going up and will be a very big problem for us, not in sort of 10% increase, but in the order of 80% increase or so. But in spite of increase in the internet traffic, which is a factor of 17, we have been able to provide the required services with only maybe a 10% increase in the total energy consumption since 2010. And that's remarkable. And it's because a lot of people have been working very hard to do this, including the introduction and deployment of so-called energy proportional computing hardware. This is another trend that we see these days having to do with artificial intelligence. Of course, this is very useful technology. Everyone is using it. It's becoming indispensable, expected only to grow going forward. But because of all the functions and services and utility that it provides to us. And because of our need to create higher fidelity or higher accuracy solutions for forecasting, decision-making, control, and so on, we are building more and more complex model. Some of the models that we use today have orders of hundreds of millions of hidden parameters, right? Or even billions of hidden parameters. And when you start training such models so that you can deploy them and use them for inference, the cost of training could be quite high. This one shows the requirement in terms of petaflop, 100 million petaflops to train some of our notable AI systems, right? So AlphaGo, FAN, or Master, or AlexNet is up there. But of course, there are a lot more complicated models these days, right? Some of the BERT models are quite large and require a lot of compute power. So this is, again, now bringing it in ways related more to CO2 emission, shows that, again, what the language modeling, training of a BERT language model will cost in terms of the carbon emission in different countries. And the reason it's different in different countries is because of the carbon mix is different between these things for the generation sources. So again, that's a big problem, expected to get worse. There is a trend, fortunately, in the recent past to try to control the size of the neural network models that we use to get high fidelity solutions through advanced architectural optimizations that one performs on neural networks, or through aggressive quantization and pruning and so on. A lot of folks in the academia and industry are focusing on those things. So hopefully it will come down. This trend is going to stop, but whether we can reverse it soon is the question. So the other source of energy consumption for with respect to IT is, of course, all the mobile and personal devices that we love and use and we depend on every day of our life. And these devices consume a lot of energy, but more importantly, their manufacturing costs a lot, right? And so if I go to the next page here, this is from Apple's sources. It's somewhat of a marketing for Apple. I took it from their document, but at the same time, it reflects at least the trends, right? So you know, every company, big company today, Fortune 500, has some kind of carbon footprint control or neutrality in mind, and advertises the same. So, for example, Apple is saying that by 2030, they will have carbon neutrality, and then they will reduce all related emissions by 75% compared to 2015. And then by, so 100% renewable electricity is going to be used. So that's one way they control their, I guess, carbon emission. But here you can see, again, if you look at the scope 1, 2, 3, so the scope 1 direct emission is low for Apple. Scope 2 electricity that they purchase is, I mean, the meaning of the white dashed line is avoided emissions. So they are claiming here that they avoided 1 million metric tons of electricity use in the year 2022. I guess it was probably year 2021 because the report came out in early 2022. So in 2021, they saved that much, or that many metric tons of carbon because they use renewable sources of energy. And similarly, they work with their suppliers. So 70% reduction compared to the status quo maybe 10 years ago, 2015, they say is the baseline. 70% reduction because of the product manufacturing, energy efficiencies, and 22% reduction in product use. So the trend is good in the way that Apple talks about. But of course, if you look at still the numbers that we have, the numbers are quite large in terms of the overall carbon emission. So this is Microsoft carbon footprint. They are showing that Microsoft in supply chain carbon emissions peaked around 2019 or so. They're bringing it down, and they do this to some extent by avoiding emissions or by doing carbon removal. They are very big on carbon removal in terms of forestry and soil enrichment and other natural processes that's used to either capture carbon or make sure that there's going to be a compensating effect because of the plantation and the trees that they're putting in. So they claim that their total emission in 2021 was 14 million metric ton of CO2 equivalent, and that they will be carbon negative because of the green at the bottom, right? Because they're doing forestry and soil and so on. And that by 2015, they would not only be, of course, carbon negative, but they would have removed any carbon emission contribution they have had since their inception, right? Again, good goals, ambitious goals. They're working on it, and good to see if that happens. So how do we actually now know the trends and some of the issues? So as a computing expert, a graduate student, researcher trying to decide how to improve the efficiency of our computing infrastructure, from devices to circuits and systems and algorithms that run on it. Of course, there are a number of different techniques. I give some of them here, right? So developing new efficient algorithms at the application level. Well-known, easy example is I want to do Fourier transform. I could use DFT. That's order n squared. If I use FFT, somebody had to develop FFT, but once it's developed, we use it. Now we go from order n squared to order n log n, right? And that's good. Another example would be I do training of a neural network, but instead of doing training using 32-bit floating point numbers, I'll do it using 8-bit floating point numbers. Or maybe I do it even using 4-bit fixed point numbers, right? Of course, there is going to be a little bit of accuracy loss, but maybe 1%, 2%, 0.5%, whatever. But maybe I can live with that because there is a lot of benefit because of the energy efficiency and carbon emission. Reducing, so I said that, developing new models of computing, stochastic computing, approximate computing, neuromorphic Ising machines. So these are usually beyond CMOS technologies that don't rely on teraflop computational power to do the work, but on a very completely different mechanism, dynamical system sort of mechanism that allows you to solve certain types of problems very efficiently. Of course, quantum computing could be the holy grail if you can develop a large quantum computing machine that can solve very difficult problems in hopefully efficiently. We don't know. I mean, that's not proven, right? The best known is still a square root n, Grover's algorithm. But the claims of quantum supremacy are abound, right? And yet to be proven. Application-specific hardware optimized for repetitive tasks. This is find the common kernel and make sure you do a really good job of the common kernel computation. A lot of the advanced energy efficiency approaches focus on that. New materials and devices that reduce carbon energy consumption and pollution. Unfortunately, that's hard to do. And with the kind of devices that we are trying to manufacture these days, 3 nanometer, 1 nanometer CMOS devices, or beyond CMOS devices, it's getting increasingly more difficult to do that. But of course, worth try, and people are doing it. And then essentially replacing physical activity with sort of virtual ones, right? And using advanced technologies for computing, including and decision making, including control, dynamic control, or AI and machine learning would help improve the energy efficiency. So these are a few examples of the AI currently being used. I will not spend a lot of time in any one of them. I just picked a sample representative of the different ways in which AI has been used to improve energy efficiency. So this is a paper published by Haymore and also one from Hosamo, 2021-2022, that describe how they have used AI to improve the energy efficiency in buildings. And mind you that this is a big source of electricity consumption in the US, for example. 1/3 of the total energy consumption in the US is due to this, to buildings, right? Building energy. So being able to control the consumption of energy here is an important one. And usually it's like when you have a water leak, a lot of water is wasted before you detect there is a water leak. And you bring somebody to fix it. So you could use AI to detect anomalies in the building electrical energy consumption, and then know at least there is a problem and go and try to fix it, right? Maybe the fix is just turn off the switch, right? Somebody forgot, but there could be more serious than that. So AI and conservation, people are using it to provide landscape connectivity for animals to move in their domain without being, I guess, hit by cars or being sort of restricted to certain area that's not doesn't have enough resources for them to live in and grow. So a study of that AI has been used in a paper by Costanza, 2019. People have used AI to identify from satellite images and some other information, perhaps exactly where the sources of the pockets of poverty are. Of course, in a country like US, where there is a lot of data, maybe that's less important, but in countries that don't have the right infrastructure or data gathering mechanisms and reporting mechanisms, this kind of AI-based, basically imaging-based analysis could be very useful to identify the pockets of poverty that require special attention. I'm sure in a case like a recent earthquake in Turkey, very, very sad, unfortunate, this kind of technology could be used very effectively also, and probably being used. So I talked about CMOS. End of CMOS law is in sight. No one argues against that now. So maybe another 5, 7, 10 years of life is left in Moore's law, and that's it. So we have to find beyond CMOS so that we could have the free lunches we have had for the last 50 years or so. And there are many different competing technologies. One that we especially like and we have been working on, and this expedition project is about, is a single flux quantum logic, superconductor electronics. And the main reason for this attraction interest is that if you look at just the switching energy consumption, CMOS versus single flux quantum versus reversible computing. So 10 to the 6 KT log N2, this is the minimum. You have to be at least 3 times that to have a signal value that you can detect. So, okay, 10 to the 6. Single flux quantum, 10 to the 3, and reversible computing using adiabatic version of the SFQ logic is order of the thermal noise. And so in the best case, 6 orders of magnitude improvement in energy efficiency. And the performance is quite acceptable, right? Even at that, for 8 UFP, we are 5 gigahertz at 4.2 Kelvin. The big problem, elephant in the room, is that you have to cool down to 4.2 Kelvin from room temperature. And that means maybe a factor of 1,000 loss in energy efficiency itself. 500, I think the Carnot cycle efficiency is about 100 or so, 100 some. But effectively, 500 would be quite good, and more realistically, probably 1,000 at the present time. In spite of that, this is still a good win. All right, so information accessibility is quite important. There are well-known studies that show information is really provided to different to people in different parts of the society based on their income or gender or race in different ways. Usually, people who have higher income, white, male, have better access to these resources, and these resources give you knowledge, power, and agility to respond. So it's very important to make sure that there is accessibility and equity in distribution of these resources and these capabilities across the society for it to prosper. Cultural sustainability, I talked about, basically a combination of the environmental issues, economic growth, and safety and healthy lifestyles, well-being of the individuals. And again, you could use a variety of different approaches to analyze this, to try to encourage more of the culturally sustainable practices, and so on. And that's beyond the scope of my talk today. So finally, being an educator and a teacher myself, and many of you are students or also faculty, we know that education will have a big value for an individual, but also for a society that have individuals well educated in technology, in sciences, and all manners of natural sciences. And so we need to have mechanisms not only for training a new generation of the workforce, but also for retraining the existing ones to make them adapt in using the latest and the best that technology offers at the present time. So I'd like to conclude my talk here. Let's build sustainability into our digital ecosystem in our future, develop society 5.0, as sometimes people talk about it, overcoming many of the issues that we face today, improving our quality of lives, but also making sure that we are not sacrificing or compromising the future of our children. Thank you.